Generative design is on the rise, with promises like widening design exploration, achieving higher performance, in addition to producing novel or unexpected solutions to design problems. If we take an overview of the generative design process, we find that it starts by defining the design space to be explored, which is followed by exploring through automated search algorithms that find the design alternatives maximizing some chosen objectives. Next, designers are tasked with navigating the generated alternatives to find the set of alternatives that best match both their objective and subjective criteria. This research focuses on analyzing the literature on data visualization tools aimed at this task, with the goal of deriving insight that enable us to design better tools in the future. Generative design produces a large number of design alternatives, and this is part of its strength, but it also creates a challenge for designers, as too many choices can in fact overload designers. One way to mitigate that is to simplify the design space first. This is what designers did in the study by Shirin et al. When they were presented with a pile of design options on physical cards, upon which designers were observed creating collections to help them make sense of the alternatives that were presented to them. But when working in a digital medium, as is the case with generative design, we can also rely on automated analysis techniques like clustering and dimensionality reduction to help us simplify the design space as argued by multiple researchers. So in this work, and motivated by the choice of a broad problem, we focus on recent tools that involve some form of design space simplification. Next, we also analyze these tools with the help of concepts from the visual analytics field. This is because the tools we survey are data visualization tools, and they address complex design datasets. The first of these concepts is a view, and a view is any visual representation of raw data. Sometimes we might have more than one view. This is because each visualization technique can reveal different aspects of a dataset, and by combining different techniques, we can understand the data from multiple points of view. To facilitate that, visualizations are usually linked to each other, such that actions on one can impact the other. In addition to that, we analyze these tools based on the hypothesis that there is a demand for tightly covering the design forms and their data in design exploration tools. This demand was voiced before by other researchers, but we found that it could be taken further. Coupling design forms and their data is important if designers were to incorporate data-driven processes without losing sight of the qualitative aspects of design that are not captured by data. The simplest way to achieve it is to include the visuals of design alternatives in the interface, but I will come back to that later. With this in mind, we use the concepts from visual analytics to systematically analyze these tools and ask questions like which of these views represent design data and which represent design forms, and in what way are these views coupled together. Now, before going to the results, let me present a few of the systems that we looked at while introducing the concepts of clustering and dimensionality reduction. Clustering is the process of grouping items based on their similarity. Ideally, we would like to place alternatives into groups that are meaningful to us, depending on what we are looking for. Clustering simplifies the design space by creating groups in it. Each group can then be represented through a single representative, like the dark trusses in this example. A variant of clustering is called hierarchical clustering, and it creates even smaller groups within each cluster, as in the examples here. Another form of space simplification is dimensionality reduction. In practice, it is often the case that parametric models have more than a dozen of different parameters. Dimensionality reduction can be used to gain an understanding of the ranges of geometric variations in the design space in a simplified representation. For example, in this work by Harding, these glyphs are controlled by 9 different parameters, but here they are mapped to a 2-dimensional grid instead, using a dimensionality reduction technique known as self-organizing maps. An important property of self-organizing maps is that if two alternatives were similar to each other in the original n-dimensional space, then they will also be close to each other on the 2-dimensional map. So to recap, both clustering and dimensional reduction depend on the computing the similarity between design alternatives. Having reviewed clustering and dimensionality reduction, we can add new questions to our analysis about which simplification technique is used, if any, and how is the similarity between alternatives computed. After an in-depth analysis of about 10 systems, we arrived at our first contribution, which states that the simplification of the design space, which relies on computing similarity between alternatives, has many phases. And this is in the sense that it can be achieved in different means, like clustering and dimensionality reduction. It can be represented in different ways, like the different ways to represent the results of hierarchical clustering, or the different ways to create and represent the result of self-organizing maps. And most importantly, that it has many applications for design space exploration. Introducing these applications requires some context, so I will introduce them by analyzing a few examples. The first is Design Explorer, and I choose this tool because it's a widely used tool in practice, even though it does not have any kind of simplification. First, we can distinguish both the form and data views. Then we can ask about the kind of interaction between them. How does one influence the other? So let's look at it in action first. So you can see that the parallel coordinates plot is used to filter the visuals at the bottom. And then we can also inspect a single alternative by clicking on its visual, which then highlights that alternative in the other views. Now what we observe here is that the parallel coordinates plot is dominating the other views and is only slightly affected by them. In particular, there are no major filtering or highlighting actions that starts from the form view. Or in other words, there are no powerful form-driven interactions. In fact, we found that most of the systems we surveyed lacked form-driven interactions, with exceptions like Dreamlands, where users can, for example, use the chisel tool to abstract away undesired forms by interacting on a semi-transparent stack of designs. We argue that form-driven interactions can open new possibilities for enacting design criteria that are hard to express in numbers. Now, Design Explorer and Dreamlands have no simplification. But how does the concepts we talked about of form and data coupling and form-driven interactions apply when simplification is involved? For that, we can look at a different system, namely Cupid. Cupid have a parallel coordinates view on the left that is mostly a data view. On the right, we have a radial tree which represents the results of hierarchical clustering of the alternatives. Each branch in the tree represents a different subcluster. Now it also happens that in the case of Cupid, clustering is performed based on the similarity in the geometry of the alternatives, as opposed to using their inputs or performance values, as is done in other systems. This means that we are in fact performing a form-driven interactions when we are interacting with the tree in Cupid. In Cupid, both views can highlight each other. But what's interesting is the interpretation of this action. For example, by hovering over an icon in the tree on the right, we highlight all the alternatives below it in that branch. Or in other words, we are highlighting a set of alternatives that are all similar to each other or share common features. This enables a different way for coupling design forms and their data, which we call similarity-based coupling. In particular, depending on the criteria used in simplification or clustering, we are able to query the performance of alternatives that have a similar form or the appearance of alternatives that have a similar performance. We provide a more detailed analysis in the paper, but for now we can go back and summarize the applications of design space simplification, which include first alleviating the choice overload problem, creating visual overviews of the design space, opening up new venues for interrelating design forms and data, such as similarity-based coupling we saw in Cupid, or introducing new ways of querying alternatives through form-driven criteria, for example, such as the radial tree, which performs a form-driven interaction that is based on similarity. This was the first contribution of the paper. The second contribution is a conceptual model. This conceptual model captures the relationships I talked about between the data and the form views, and how simplification relates to all of that. This model may help in analyzing other systems through the same lenses that we use in this paper. Now, if you recall, the goal of our research is to generate insight that would help us in designing better tools in the future. And these tools are aimed at exploring the outputs of generative design. This brings us to our last contribution. With this understanding of the applications of design space simplification, and with the help of the conceptual model we developed, we created the first prototype of a design analytics dashboard. This dashboard includes data and form views, in addition to a view representing a simplification of the design space through hierarchical clustering. These views are coordinated through a combination of filtering and highlighting. We discuss this interface in detail in the paper, as well as the decisions we made in more depth. In conclusion, we presented our process for analyzing several tools for exploring design spaces. We discussed the lenses we used in analyzing them, and finally we presented our contributions, which include a better understanding of the role that simplification can play in design space exploration, or in other words, the fact that design simplification has many faces, a conceptual model for analyzing these tools, which include concepts like form-driven interactions, and an initial prototype illustrating some of the concepts we discussed. In the future, we intend to continue iterating on and evaluating this dashboard, as well as exploring the practical and the design-specific concerns surrounding similarity-based exploration. Thank you for listening.